will come back to this second half of today's lecture. Just now I proved a theorem, the Artinian implies Noetherian, the Jacobson radical is nilpotent, and the number of maximal ideals in Artinian ring is finite. So, I want to note one important corollary. So, let K be a field and A be a finite K algebra. Remember, when I write finite K algebra, that means the module A as a modulo over this ring A, this ring K is a finitely generated, and because in this case K is a field, this finite algebra will simply means dimension of A as a K vector space is finite. So, let us call it n. In this case, then the cardinality of the set of maximal ideals is less equal to this dimension of K as a vector space over K, and K spectrum, I hope you have not forgotten, because it is for a while we have not talked about it. This is also less equal to dimension of K over A over K. Alright, what was the K spectrum? K spectrum, so proof, recall that K spectrum of a K algebra is precisely all those maximal ideals in A such that the residue field is isomorphic to the field K as K algebras, and therefore, this set is contained in SPM, and we have seen examples where it may not be equal. Alright, so therefore, if I have to prove both these inequalities, I will only have to prove one of them. I will only prove this one, and because this cardinality will be bigger equal to this, that will also follow. So, it is enough to prove that cardinality of the set of all maximal ideals is less equal to dimension of A over K. Alright, so how do we prove this? Remember, while proving the above theorem, so remember that in the proof of above theorem, we noted the following. If M1 to MR, M1 to MS are different maximal ideals, are distinct, then we have constructed, I will write on the next page, then we have constructed a strictly descending chain. So, A contained in not equal to M1, contained in not equal to M1, M2, and so on, at least till M1 to MS, and therefore, and each stage the residues that M1 Mi minus 1 mod M1 Mi, this is for I equal to 1 to S, these residue modules, they are A by Mi vector spaces, because they are annihilated by Mi. Therefore, and because it is strict here, this has to have one dimension at least, and hence dimension over A by Mi M1 to Mi minus 1 by M1 to Mi, this is bigger equal to 1, because it is strict here. This is non-zero, and therefore dimension of a non-zero vector space is at least 1. So, at each stage dimension is 1. If this dimension is 1, then this the dimension over k is even bigger, because this dimension is bigger equal to dimension of over k of this M1 to Mi minus 1, M1 to Mi, this because k is contained in A by Mi. So, if the dimension of a bigger, so these are vector spaces over k also by restriction, and this dimension will be more. The dimension I wrote the other way. So, this dimension is more, because k is a smaller field. For example, a real dimension is more than the complex dimension. So, therefore, these are also not bigger equal to 1. So, at each stage is bigger equal to 1. From this and from this observation, we get dimension of k over A is bigger equal to the number of steps here. So, that is S. So, which is what we have called the cardinality of this maximal ideals of A. So, this all right. So, and for the other assertion, so this proved this one, but I wanted to prove for more. I wanted to prove, I don't have to prove, because this cardinality is always bigger equal to the cardinality of the K spectrum. But also we can prove directly this. So, direct proof, so another proof if you like, proof of this inequality, this directly proof of cardinality of K spectrum of A is smaller equal to dimension of A. I write another proof. So, K spectrum, you note that that is also same as home K algebras from A to K, from here to SPM A. I give you a map. So, the map, what is the map? Take any homomorphism, K algebra homomorphism from psi from A to K, K algebra homomorphism, and map these to kernel of psi. Kernel of psi is a maximal ideal. So, therefore, it makes sense, and I want to claim that this map is injective. That is because, how do you get back? So since if I take k is k times 1A, this is a sub of A. So, all elements, this is a copy of k contained in A, and if I add this kernel, this, what do I get? This is a maximal ideal. Therefore, any element if I add it, I get A. So, this is A. So, because of this, the map is injective, because two psi and psi prime, they cannot go to the same M, because if they do, then this happens, and therefore, the map is injective, and therefore, we have actually proved that this cardinality is smaller or equal to this cardinality. So, what we have proved is not so I have proved the fact that this cardinality is smaller or equal to cardinality of SPM of A. But these are already we have proved, one is a subset of other, so we did not have to prove that, but anyway this was also interesting fact, so I mentioned it. Now I want to switch back to modules and generating systems, and I want to study ultimately modules over a local ring and prove a very important lemma called a Nakayama lemma. So, let me start right away with what I want to prove. Now, we want to prove very important lemma. This is called, actually it is called Krull Nakayama lemma. So, let A be a ring and A be an ideal in the ring A. Then the following are equivalent. One, A is contained in the Jacobson radical, MA. This is the Jacobson radical of A, and 2, for every finite A module V, remember finite means there exists a finite set of generators for V. It is finitely generated module over A with V equal to A times V, that implies V is 0. So, proof is very simple, and I will deduce some consequences from this lemma. Proof, I want to prove first 1 implies 2. Alright. So, we have given it as a finite module, that means there is a finite generating system for V. So, let V equal to AX1 plus AXN with these elements x1 to xn in V. That is a set of generators for V, finite set of generators for V. That means every element of V is a finite A linear combination of x1 to xn, and choose n minimal and n minimal. That means there is no generating system for V which has lesser number of elements than V, a lesser number of elements than n. Alright, so what does this mean? So, and I want to prove that if V equal to AV, then V is 0. So, suppose V equal to AV, but V is not 0, then we should get a contradiction. So, V is not 0, so therefore there is at least one non-zero element there. So, let 0 which is not equal to x be an element in V, then this x, actually I can take that to be x1 only. See, none of these guys are 0, because n is minimal. If any one of them is 0, then you don't need, and that means n is not the minimal. So x1 has to be non-zero, and in fact all other has to be non-zero, because if any one of them is 0, then you don't need that in a generating system. Okay, so x1 is non-zero, but x1 is in V and we have this equality. That means this x1 I can write a combination of x1 to xn, but element, the coefficients are not only in capital A but in the ideal A. So this I can write it as a1 x1 plus 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 a n xn, which is same thing as saying, so that is, I will rearrange this equation. I will bring this 1 minus a1 x1 on one side, and the other side I will keep it the same, x2 plus a n xn. But now look at this side, this element, because where is a1, so all the elements, this, when I wrote this a1 an, all of them are in the ideal A, and this ideal A we are assuming it is contained in the Jacobson radical by assumption 1. Therefore, this 1 minus a1 is actually unit in the ring A, because this a1 is in A. Therefore, this is unit, and therefore I can multiply this equation by inverse of that, and then we get x1 equal to 1 minus a1 inverse a2 x2 etc. etc. a n xn. That means this generating element I can write in terms of the others. So that means we have proved that V is generated by x2 up to xn, but this contradicts the minimality of n, a contradiction to the minimality of n. So that proves 1 implies 2. Now let us prove 2 implies 1. 2 implies 1. Alright, so what do we have given? So I want to prove that 1 is, so to prove that A is contained in the Jacobson radical. So suppose not, that is A is not contained in the Jacobson radical, then I want to contradict 2. That means I want to produce a module which is a finite module where V equal to this ideal A times V, but V is non-zero. So if this is not contained, then A will not be contained in at least one of the maximum ideal for some m in SPMA, because if A is contained in all of them, then A will be contained in the Jacobson radical, because since MA is by definition intersection M belongs to SPMA. So therefore it is not contained in that maximal ideal. And now take V equal to A by M. This is obviously an A module, and finite also. In fact, it is generated by one bar, which is the image of 1 under the residue map. So it is actually a cyclic module, and what is this is obviously non-zero, because maximal ideal never a unit ideal, and what is now A times V, this is A times A by M, and A is not contained in M, therefore this is, so this is precisely A plus M modulo M. But A plus M is, because A is not contained in M, this has to be the whole ring, because this is M is maximal and this is something which is not contained there. Therefore this is A by M, since A plus M is the whole ring A, because this contains properly M. This is because A is not contained in M, therefore, and this is V. Therefore I have checked that AV equal to V, but we know V is non-zero. So a contradiction. Contradiction to 2. So that proves 2 implies 1 also. Alright, so some corollaries I will deduce. Corollary 1. So suppose U is contained in V, B, A modules. Let these be A modules such that the residue class module V by U is finite. V may not be finite, but V by U is finite. Finite means finitely generated, finite A module. And suppose A is an ideal which is contained in the Josephson radical of A. If U plus AV equal to V, then V equal to U. Proof. Apply Nakayama lemma to the module, to the A module V by U. I want to show this is 0. This is 0 equal to saying that this equality. So to show that it is 0, I will check the condition, second condition there, which is, so enough for this. For this, enough to prove that A times V by U is same thing as V by U, and then that will imply by Nakayama lemma V by U is 0, and that is equivalent to saying V equal to U. So how do you check this? So this is because, how do you write this quotient? So this is same thing as because this A times V may not contain U. So the numerator will be now U plus AV modulo V, and these two modules are equal. Now this is contained here, this contains U, this contains U, and therefore by correspondence theorem, by correspondence theorem on submodules, so I will not write more, we get, no, already implies I have written. So this by correspondence theorem the numerators are equal. So U plus AV equal to V, that is what we have given. So therefore this equality. So because of this I should correct myself, not because of the correspondence theorem. This equality, this equality follows from the assumption this is the assumption. Therefore I have this equality, and therefore by Nakayama lemma then I can conclude V by U is 0, but that is equivalent to saying V equal to U. So that proves the corollary. So corollary 2, let f from V to W be an A module homomorphism such that co-kernel of f, which is by definition V mod W modulo the image of f, that is W modulo f of V, is finite. That means it is a finite A module, is a finite A module that is given further. Let this is A be an ideal contained in the Jacobson radical of A be such that the induce A by A module homomorphism f bar from V by AV to W by AW. So, what is this defined by? This is x bar going to f of x and then bar, and then note that this should be well defined. This is well defined. This is the induced homomorphism from this f. This is A by, both are A by A modules, such that, so we have assumption that A is contained in the Jacobson radical and this induced homomorphism is surjective. Then f is already surjective. F is also surjective. So, we will write down the proof and we will have to use Nakayama lemma in the proof. So, proof. All right. So, f bar is surjective, that is given. So, therefore, image of f bar is equal to W by AW. On the other hand, this image of f bar is precisely by definition is f bar of the whole V by A, V by AV. But this is same thing as FV plus A times V, not these are in W. So, A times W modulo AW. See, this I have to write this because this FV may not contain AW. Therefore, we have to always write, if you want to write the submodule of the quotient module, then it is of this form. So, these are equal, therefore, the numerators are equal. So, therefore, W equal to FV plus AW, but then because A is contained in the Jacobson radical by, and this is co-kernel F is by definition W modulo the image of G, image of F, which is W by F of V. So, this is finite that is given, and A is contained in the Jacobson radical given. Therefore, by earlier corollary, this, what do we conclude? You conclude W equal to FV. This is U and this is, I am applying to this submodule of W. So, this is by corollary 1. So, this, but what does this mean? This means F is surjective. All right. So, we will apply Nakayama lemma to say something about minimal number of generators for a module over a commutative ring. So, let us recall. So, as usual our notation is let A be a commutative ring and V be an A module. Then we have defined earlier what is the minimal generating system for V. That is the generating system for V from where we cannot drop any element of that system. That means no proper subset of that generating system should generate V. Such a system is called a minimal generating system for V. That we have used this term earlier also. And now this is the minimal number of generators for V. That means among all the system of generators, you take all system of generators and take their number in that, and that is you take the minimum among them. So, therefore, what I am saying is put mu A V by definition min of all the cardinalities such that V should be generated by this system Xi, where these Xi's they are elements of V. And note that these minimum exist. I will just note here, these exist by well ordering principle on cardinal numbers. This case occurs when your module is not finite over A, then only the problem comes. So, for us, if V is a finite A module, then mu A V is always bounded by the cardinality of any generating system. So, cardinality I, where Xi I in I is a generating system for V. That is clear because we have taken the minimum of this. So in case where V is a finite A module, this number is always a finite number. This is an integer. This is a natural number. So in particular, in this case, mu A V is a natural number. In this case, of course, V is a finite module. And now I want to compute this number precisely when A is a local ring and V is a finite module. So, before I do that, just to get a little feeling, what you observe that this, for example, if you take a ring, base ring to be Z and V is also Z, then we know that mu Z Z is 1. because 1 is a generating system and Z has to need at least one generator. So, this is one is clear, but also note that if I look at the set 2 comma 3, this is a generating system. For V, for Z. So, it has two elements. So, the above inequality is crude, because I said that mu Z, Z is less equal to 2. If I would have taken some other generating system, in fact, in this case, you can find out, given any natural number R, there exists M1 to Mr integers such that M1 to Mr is a minimal generating system for Z. So, that is very, this is very probably one has to do with an exercise. So, but now I want to be little bit more specific, and therefore, these examples also show that we have to put some condition on the ring, then only we are going to get better result. So, our assumption now is, let A comma M be a local ring and V be a finite A module. Then first I want to prove this proposition, which will be a consequence of lemma of Nakayama, which I had proved in this lecture earlier. So, which says that, so given, so we have this assumption. So, for elements x1 to xn in V, the following are equivalent. The following are equivalent. So, 1 x1 to xn generates V, and 2 x1 bar xn bar, where these are the images of x1 to xn in the residue class module M by V by MV. This generates V modulo MV as A by M vector space. So, if you want to check some system generates V, we have to check that the modulo M times V they generate. So, let us see the proof. Proof is really very simple. So, first of all, 1 implies 2 is trivial. Conversely, 2 implies 1, we need to prove. For 2 implies 1, let us put V bar equal to V by MV, and let us also put A bar is this A by M. These are the residue class structures. Now, what we have given, we also look at the map, and W, let us put W is the submodulo of V generated by these x1 to xn. This is a submodule, A submodulo of V. And now we look at the exact sequence, W by MW to V by MW and to the mod now. this mod this. So that will be precisely V bar by M V bar to 0. This is the exact sequence, and this map is what? What is this map? This is the, of course, this is the co-kernel of this map, and this map is, this is F bar. This map only, I only have to prove, send where xi goes, xi bar, that goes to xi bar. So that means image of xi mod mw, that goes to image of the same xi mod this. This is the map, and the fact that this module is generated by these xi's bar, that is given to us by 2. So that will simply mean that this xi bar belongs to the image of f bar for all I from 1 to n. That is because by 2, by assumption 2. That means this f bar is already surjective. So therefore this has to be 0. So that implies V bar by M V bar is 0. But this V bar is a finite module. And so this means V bar is finite and this equality holds. But we are over a local ring. V bar is finitely generated, V bar is finite and local. So that will imply by Nakayama lemma V bar is 0. This is by Nakayama lemma. But V bar is 0 means what? So that is V equal to W. Maybe I have made an I will just want to check that. I think I want to this definition. So I want to erase this. So V bar is V by W. So note that this sequence is exact, where this map f bar is given by just image of xi goes to the image of xi in appropriate residue class module, and then that proves this is 0. So that means V, so this is, that is, this proves 1. So that proves the equivalence of 1 and 2. But I want to write important consequences of this, which are very, very important and often used. So it's better to record them. So corollary 1. For elements x1 to xn in the module V, as earlier notation, V is finite and ring is local. The following are equivalent. 1, x1 to xn is a minimal generating set for V, and 2, x1 bar, xn bar, these are elements in V by MV, images of x1 to xn modulo M times V, is a by M basis of the A by M vector space P by MV. So this is obvious from the earlier one. So let me write another corollary. Corollary 2. Mu time the minimal number of generators for V is precisely the dimension of the vector space V by MV as a by M vector space. This is what we proved in the earlier corollary. In particular, if M, the ideal, is finitely generated, then the minimal number of generators for the maximal ideal of the ring A is dimension of the vector space A by M, M by M square. This is also called embedding dimension of the ring. Embedding dimension of the ring A. This is the notation. This is the term used for this. So that was corollary 2. One more and then we will stop. Corollary 3. So given R elements in a finite module over a local ring, has the same notation, they can be extended to a minimal generating set. So the statement is x1 to xr can be extended to a minimal generating system for V if and only if the residue classes x1 bar, xr bar in V by MV are linearly independent over A by M over the residue field of the local ring. So this is also immediately follows from the earlier one. In particular, if you have one element x in V, that can be extended or can be completed to a minimal generating system for V if and only if this x should not be 0 in modulo V by MV. So that means this x should not be in M times V, because this is equivalent to saying that is x bar is not 0 in the vector space V by MV, and then we know if you have a non-zero vector in a vector space that you can always complete it to a basis. So that proves. So with this I will stop this, and from the next lecture onwards I will prepare for proving a very important connection between commutative algebra and algebraic geometry, namely Hilbert's Nullstellensatz. So thank you very much. We will continue in the next week. Thank you.